Hi all, welcome to another video of the subject power system analysis based on the KTU syllabus, and we are on module 3, and today we are going to discuss the load flow solution by Gauss-Seidel method. The Gauss-Seidel method is an iterative algorithm for solving a set of nonlinear equations, load flow equations. So before going to that, just I am reminding some terms, that is different buses we are using: load bus, generator bus, and slack bus. Just we are recollecting the terms. That is, for load bus, the specified values are P and Q. The quantities to be obtained are the voltage magnitude and its angle delta. Okay, for generator bus, the real power P and voltage magnitude are specified. We have to find the reactive power Q and angle delta. And for slack bus, delta V, mode V and delta are specified, and we have to find P and Q. Okay, so as we know the Gauss-Seidel method, okay, it is used to solve the load flow equations, okay, nonlinear load flow equations. And we know the equations as we already learned in the previous video. Okay, that is the bus voltage or node voltage Vp is equal to 1 by Ypp into Pp minus jQp by Vp star minus sigma q equal to 1 to P minus 1 Ypq Vq minus sigma q equal to P plus 1 to N Ypq Vq. Okay, this is the basic equation we are using here, and here the values of P may be 1 to etc up to N based on number of buses we are using. If it is a 4 bus system, the values of P may be V1, okay, V1, V2, V3 and V4. We have to find all these values V1, V2, V3 and V4 by doing some iterations. Okay, so like that. So here the variables in the equations, okay, here in the variables in the equations, for P is equal to 1, 2, 3, I already said that it is V1, V2, V3 etc up to Vn. Okay, are the node voltages here, that is the bus voltages here. So in Gauss-Seidel method, an initial value of voltages are assumed, okay, before starting the iterations. Okay, we are assuming an initial values of the voltages. Okay, that is normally we will taken the initial values are 1 plus j0. Okay, the voltages 1 plus j0. Okay, that is the initial values like v1 0, v2 0, v3 0. Okay, that is before the first iteration. We will, if it is a 4 bus system, we will assume the initial values of the bus voltage or node voltage as v1 0, v2 0, v3 0, v4 0, like that. Okay, and for doing the problem, and we will assume that values equal to 1 plus j0, and we will start from there. Okay, so that is the first step normally we will do before the starting of the method. Okay, before the starting of the problem. And the process of computing all the bus voltages, okay, are explained as the one iteration. Okay, the iterative process is then repeated till the bus voltage converges within prescribed accuracy. Okay, that is the all the bus voltages should be, okay, should be in between a prescribed accuracy. Okay, so after doing 1, 2 or 3 iterations, okay, we may be getting the correct answer after 2 or more iterations, like that. Okay, so we have to repeat the entire process up to till we are getting the values in the prescribed limit. Okay, so based on the practical experience, it is easier to get a set of initial voltage very close to the final solution. Okay, that is here we are assuming the values of v10, v20 as 1 plus j0. Okay, but if you are having a practical experience, we can assume, okay, far better, okay, better values for v10, v20 at the initial stage. Okay, that is near to our final solution. Okay, so we can write the modified form of this equation. Okay, modified form of this equation as Vpk plus 1 is equal to 1 by Ypp, Pp minus jQp Vpk star minus sigma q equal to 1 to P minus 1 Ypq Vqk plus 1 minus sigma q equal to P plus 1 to N Ypq Vqk, where Vik is the kth iteration values of bus voltage Vi, and Vi k plus 1 is the k plus 1th iteration values of bus voltage Vi. Okay, so here for doing the first iteration, we will keep the k is equal to 0. K equal to 0 means that is we will get Vp1. Okay, in substituting here we will get Vp1, that is the first iteration value. So we have to find all the bus voltage for at the initial in the first iterations, that is V11, okay, V21, V31, like that. Okay, for all the buses we have to find the first iteration value, and after that again we have to repeat for the second iteration. Okay, doing by using the same equation. Okay, here one thing you have to notice that to compute the k plus 1 iteration, okay, to compute the k plus 1 iteration of a bus voltage P, okay, of a bus P voltage, the k plus 1 iteration values of voltage are used for all buses less than, okay, for all buses less than P, and kth iteration values of voltage are used for all buses greater than or equal to P. Okay, so that is for example, okay, if there it is a 5 bus system, okay, assume it is a 5 bus system. Okay, so we have to find in the first iteration level, we have to find the V31. Okay, suppose we have to find the V31. Okay, V3 is the third bus voltage and 1 stands for the first iteration. Okay, V31, we are going to find the V31 using this equation. Okay, so in that case we have to use, okay, we have to use V21 and V11, okay, because the values of P, okay, here the values of P 2 and 1 is less than 3. Okay, so we have to use the k plus 1 iteration. Okay, k plus 1 means 1. Okay, that is here we are computing the V31, that is the first iteration values of the bus voltage 3. Before that we may be, okay, of course we will be finding V21 and V1. Okay, this is already with us. Okay, so for finding V31 we have to use V21 and V11. Okay, because the value of bus, okay, bus is less than 3. Okay, and we have to use V40 and V50. Okay, because here the values of P, that is bus number P, is greater than 3. Okay, so we have to use the kth iteration values. Okay, V40 and V50. Okay, actually we will be substituting these values in our equation. Okay, in this equation. Okay, so it will clearly understand if you are doing a problem. Of course you have to see the next video. In that I will explain the problem well. Okay, so comparing these two videos you will clearly understand what is a Gauss-Seidel method. Okay, so you have to see the next video also, okay, for doing the problem. So that's the point I have mentioned here, that I have written here. Okay, that is the k plus 1 iteration and kth iteration, like that. So one important thing is that the slack bus, we are taking the slack bus as a reference bus. Slack bus, it is a reference bus, and so its voltage will not change. Therefore in each iteration the slack bus voltage is not modified. Okay, so normally the slack bus voltages may be given initially. Okay, that is 1.24 plus j something. Okay, j 0.1. so we have to take these values. Okay, we will not change the slack bus voltage at the stage of any iteration. Okay, it will keep on constant. That thing you have to keep in mind. Okay, and for the generator bus, okay, for the generator bus the reactive power is not specified. Okay, for the generator bus the specified values are P and mod V. We have seen that in the previous slide. Okay, P and mod V. The values of Q is not specified. That we have to find in the case of a generator bus, if the generator bus is present in the problem. Okay, so normally we can split the problem into two cases. Okay, two different cases. That is, the first case we assume all the buses other than the slack bus are PQ buses, that is load bus. Okay, in the second case we assume the presence of both the PQ and PV bus, that is load bus and generator bus other than the slack bus. Okay, so we can split all the load flow problems into mainly into two categories. Okay, one is with the slack bus and PQ bus only, that is load bus only, and another one is with the slack bus and PQ and PV buses. Okay, so if our problem contains a generator bus, the reactive power is not specified. Therefore, in order to calculate the phase of bus voltage of a generator bus using equation 2.17, that is equation 2.17 is this one. Okay, this is equation 2.17. We have to estimate the reactive power from the bus voltage and admittance as shown below. Okay, that is we have to find the reactive power for the generator bus. That's all. Okay. So for finding the reactive power, we are using this equation, okay, and from that by rearranging and all, Pp minus jQp is equal to this one, and here the reactive power, that is Qp is the imaginary part of these values. Okay, imaginary part of these values. Okay, that is if after calculating this equation, if we get 1.24 minus j 1.5, we have to take the reactive power Q, okay, as minus of minus 1.5, that is 1.5. We will take the values of Q as 1.5. Okay, it is clearly written here. Okay, that is Pp minus jQp. We have to find the Qp. Okay, so the Qp, the equation for Qp can be written as Qpk plus 1 is equal to minus of imaginary part of this equation. Okay, this is the equation. So after finding this, we have to take the imaginary part, and that is negative of the imaginary part. That will be the reactive power of bus P during k plus 1th iteration. Okay, and one more thing is that is we have to find the slack bus power and line flows. Okay, slack bus power at last. Okay, in the question itself they may be asked to find the slack bus power. Normally we know that for the slack bus, mode V and delta may be specified. Okay, we have to find the power flow. Okay, power and line flows. Okay, so for that we are using this equation Pp minus jQb. It can be, okay, shortly written as like this. Okay, this under equation. Okay, this under equation can be written as like this. Okay, Pp minus jQp, that is Q equal to 1 to n. Okay, if you are writing this equation, we are splitting that the values of Q. Okay, values of Q to 1 to P minus 1 and P plus 1 to n, like that. Here we are writing it together. Okay, and for finding the power, okay, slack bus power, okay, normally we will be considering a pi network transmission line. Okay, here consider a line connecting bus P and bus Q, okay, using a transmission line. Okay, and it is having the transformer at both ends. The pi equivalent of the transmission line is with the transformer at its ends consists of a series admittance YPQ. Here you can see this is a series admittance YPQ, and shunt admittance as YPQ dash by 2 and YPQ dash by 2. That is for constructing a pi network. Here we are using this concept. Okay, and based on that we will be finding the slack bus power. Okay, here the current, okay, that is IPQ can be written as IPQ1 plus IPQ2, IPQ1 plus IPQ2, also IQP as IQP1 plus IPQ2. Okay, so here the IPQ1 can be written as VP minus VQ into IPQ. Y is the admittance, that is normally we will be writing VP minus VQ by ZPQ. 1 by ZPQ is the YPQ here. Okay, plus VP into IPQ dash by 2. So the complex power injected by bus P in line PQ can be written as SPQ is equal to PPQ minus JQPQ. Okay, that is also equal to VP star into IPQ. So IPQ can be written as like this. From that VP can be find SPQ. Okay, and also in the right side IQP is the IQP1 plus IQP2. Okay, so IQP1 plus IQP2, same as we can write the equation as VQ minus VP into IPQ and plus VQ into YPQ dash by 2. So the complex power injected by bus Q in line PQ, SQP is equal to PQP minus JQP is equal to VQ star into IQP. So VQ star into IQP, we have already found the values of IQP, so just written here. Okay, so the power loss in the transmission line PQ can be written as SPQ loss is equal to SPQ plus SQP. Okay, so this is a slack bus or normally power normally we will be finding in the problem. Okay, sometimes in the question they may not be asked to find the slack bus power, so in that stage you need not to compute these entire equations and all. Okay, and we can simply write the entire procedure for Gauss-Seidel method by using some steps. Okay, at least try to these steps. Okay, that is around 13 steps are there. Okay, so if you can find these steps, it will be better. Okay, so if a question asks to write the procedure for load flow equations, we have to write these steps only. Okay, I have mentioned all other cases before. Okay, all these cases for understanding the base of the Gauss-Seidel method, the equations we are using, actually you have to find these steps. Okay, so the first step I have already said that assume a flat voltage profile of 1 plus J0 for all buses except the slack bus. Okay, the slack, because the slack bus voltage may be given in the question. Okay, be given in the table itself. So for all other buses we are assuming the voltage, initial voltage profile as 1 plus J0. Okay, and the second step is assume a suitable value of epsilon, okay, called convergence criterion. Okay, that is, I have said that the voltages, all the bus voltages, okay, should be, okay, between a certain limit. Okay, that is by calculating, by doing number of iterations and all, we will find the change in voltages. Okay, change in voltages, and if it is within the convergence criterion, we can stop the iteration. Okay, so here the epsilon is a specified change in the bus voltage that is used to compare the actual change in bus voltage between kth and k plus 1 iteration. Okay, that is first and second iteration we will calculate the voltage change. Okay, and if it is within the prescribed limit, we can that is if it is less than these values of E, that is epsilon, we can stop the iteration. Okay, and next step is 3, that is set iteration count k is equal to 0, and assumed voltage profile of the buses are denoted as V10, V20, V30, like that. Okay, and step 4, set bus count p is equal to 1. First we have to find the first buses. Okay, first bus, and step 5, check for slack bus. If it is a slack bus, then go to the step 12. Okay, because we know that for a slack bus its voltage will not change. Okay, its voltage will not change. So if it is slack bus, we have to go to the step 12. Actually the step 12 means we are incrementing the bus and again checking for it is a slack bus or any other buses. Okay, that is select tool is repeat the step 5 to 11 until all the bus voltage have been calculated. For this, increment the bus count by 1 and go to step 5. Okay, so step 6, check for generator bus. If it is a generator bus, go to next step, otherwise go to the step 9. That is, if it is a load bus, we have to go for step 9. Okay, and if it is a generator bus, we have to temporarily set the VPK value as VP specified. Normally the bus voltage V1 will be specified. We have to take the values of VP as VPK, and phase of VPK as the kth iteration value if the bus P is a generator bus where VP specified is the specified magnitude of voltage for bus P. Then calculate the reactive power of the generator bus using the following equation. Okay, that is I have already mentioned earlier. For a generator bus, we have to find the reactive power. Okay, reactive power. So QP calculated k plus 1, we have to use this equation. Here Im stands for the imaginary part that we know. So the calculated reactive power may be within specified limit, that is in the question itself. Okay, if it is a generator bus, we know that normally the values of P and mode V will be specified. Okay, we have to find the Q and delta. Okay, actual values of delta. Okay, so here the value also in the question itself there may be specified some limits for Q, that is the values of reactive power should be between 0.5 and 1.5, like that. There may be some limits. Okay, if the reactive power may be within the specified limit, okay, or it may violate the limits. Okay, so if the calculator reactive power is within the specified limit, then consider the bus as generator bus and set qp is equal to qp calculated k plus 1 for this iteration, and go to next step 8. Okay, if the calculator reactive power violates the specified limit, that is if it is it is not within the limit um, for reactive power, then treat this bus as load bus. Okay, we have to treat the generator bus as load bus. The magnitude of the reactive power at this bus will correspond to the limit it has violated. Okay, that is, we have to consider the generator bus as load bus if it is violates the limit, and we have to find the values of q as like this. Okay, we have to take the values of q as like this. That is, if the calculated values of q, okay, is less than the qp minimum, that is minimum and maximum value may be specified in the question itself. It is less than the qp minimum, then qp can be taken as qp minimum, and it is greater than qp max, then qp can be taken as qp max. Okay, so since the bus is treated as load bus, take actual values of vpk for k plus 1 iteration and all. Okay, and here we have specified that if it is a if it is within the specified limit, if it is within the specified limit, you have to go for step 8. So in the step 8, okay, we have to find the values of delta. Okay, values of delta. For that we have to calculate this equation. Okay, a temporary equation, vp temporary k plus 1, and from that we can find the values of delta, that is by taking the imaginary time. Okay, that is the tan inverse of imaginary part of this one, and by real part of this one we have to find the actual value of delta. Okay, so this value of delta can be taken as the vpk plus 1 values of delta. So vpk plus 1 can be written as vp specified. Okay, that is already given in the question, vp specified angle delta p k plus 1. Okay, and in the step 6 we have said that if it is a load bus we have to go for step 9. So in the step 9, for the load bus, the k plus 1, the iteration values of bus p voltage vp k plus 1 can be calculated using this equation, that is v21 v31 if like that. Okay, we have to calculate the bus voltage for load bus using the equation. We have to calculate the bus voltage, and after finding that, we have to use an acceleration factor. Okay, that is for making the convergence factor faster. Okay, for the faster convergence we have to use an acceleration factor alpha. So the real, okay, so the vp acceleration k plus 1, okay, vp acc k plus 1 acceleration values of k plus 1, that is it is the real and required values of vp can be find using the equation vpk plus alpha into vpk plus 1 minus vpk. Okay, here alpha is the acceleration factor, then set vpk plus 1 is the vp accelerator k plus 1. Okay, this can be taken as the vpk plus 1 values. Okay, so step 11, calculate the change in bus voltages using the relation. Okay, that is after finding this vp k plus 1 we have to find, okay, that is if this vp k plus 1 is 1.24 plus j 0.1, and vpk we have already found initially, vpk is 1.14 plus j 0.2. we have to find the difference. Okay, that is delta p k plus 1. Okay, that is the step 11. Okay, and step 12 we have to repeat, and step 5 to 11 until all the bus voltages have been calculated. Okay, after that we have to find the changing, okay, change between the bus voltages, delta v1 k plus 1, delta v2 k plus 1. Okay, and we have to find the largest change here. Okay, that is delta v max. Okay, that can be taken delta v max. Check whether this largest change delta v max is less than the prescribed tolerance epsilon. If delta v max is less than epsilon, then move to the next step, otherwise increment the iteration count and go for the step 4. Okay, this is step 13. And at last we have to find the slack bus power and line flows. We have already seen before in this video. Okay, and the entire procedure can be, okay, drawn like a flow chart like this. Okay, in the flow chart we have explained all these steps. Okay, so you have to find this flow chart also. Okay, that is, if we can find this flow chart, you can remember each and every steps easily. Okay, so it is something different to see. So I have just zoomed each part. Okay, each part here. You can see we are taking the initial values of 1 plus j0 and all. Okay, you can read this. Okay, and in each step we will check for the slack bus, generator bus, and for generator bus we will calculate whether the reactive power is within the specified limit, that is less than the QP minimum and the QP max, like that. Okay, and we will calculate the change in voltage. Okay, all are we have already discussed in the steps. Okay, procedure. After calculating this, delta V will increment the bus count. Okay, and at last, if that delta V max is less than the specified value, okay, limit, convergence limit, we can stop the iteration. Okay, I hope all of you understand this Gauss-Seidel method well. Of course, you have to see the next video, that is the problems. Okay, we will discuss the problem. Okay, so in that you will clearly understand how we can proceed a Gauss-Seidel load flow analysis. So thank you.